In this video, we are going to talk about finding the nth root of a complex number. For example, let's assume that we have a squared equals 4. We find a by finding the square root of both sides. So a is equal to plus or minus 4. Let's assume that a cubed is equal to 8. Then a is equal to the cube root of 8, and therefore a is equal to 2. In the same vein, if we have a exponent 4 is equal to 81, then what we can do, we can find fourth root of both sides. And therefore a is equal to the fourth root of 81. A is equal to 3. So if you have a complex number z, and we have another complex number such that w exponent n is equal to z, and we want to find the number w, then w is equal to the nth root of z, where z is a non-zero complex number. The formula for finding the nth root of a complex number is given by w equals the nth root of r times cos into bracket theta plus 2k pi divided by n. So this is wk, then plus I sine into bracket theta plus 2k pi divided by n, bracket close. Determine the solution of the equation z squared equals 2 plus 2 root 3i. So z squared is equal to 2 plus 2 root 3i. So the first thing we need to do is to convert 2 plus 2 root 3i in polar form. And we do that by first finding r. R is equal to the magnitude of z, and that is equal to 2 squared plus 2 root 3 squared. This is equal to square root of 2 squared is 4 plus 2 root 3 squared is 4 times 3. And this is equal to square root of 4 plus 12. And this is equal to square root of 16, which is equal to 4. So therefore r is equal to 4. Then now let's find the argument. Argument of z. It is equal to, however, to find the argument we need to sketch the complex number. So this is the real part of z, and this is the imaginary part of z. So it is 2 plus 2 root 3i. So let's assume here is 2, and let's assume here is 2 root 3. And 2 plus 2 root 3i will be somewhere here. So this place is z equals 2 plus 2 root 3i. So let's draw this line. It makes an angle theta with this, and let's complete it. So you can see that tan theta is equal to opposite, and the opposite is 2 root 3 over adjacent, and the adjacent is 2. So these 2 and 2 can cancel. So theta is equal to tan inverse of root 3, and therefore theta is equal to 60 degrees. But we need to convert theta into pi radians, and we do that by multiplying by the factor pi over 180 degrees. And therefore theta is equal to pi over 3 radians. So the complex number z is written as, remember we said a complex number is z equals r into bracket cos theta plus I sine theta. So z is equal to 4 into bracket cos pi over 3 plus I sine into bracket pi over 3. And therefore this implies that z squared is equal to 4 times cos pi over 3 plus I sine to bracket pi over 3. But remember that we said a complex number, the root of a complex number, wk, is given as square root of r n times cos into bracket theta plus 2k pi divided by n, then plus I sine into bracket theta plus 2k pi divided by n, bracket close, where n is the square, and then k goes from 0, 1 to n minus 1. In this case, 2 minus 1 is 1, so that means that the values of k will only do k equals 0 and k equals 1. So in this case, z is equal to square root of r is 4, then times cos into bracket theta is pi over 3, then plus 2k pi divided by n, and n in this case is 2, then plus I sine into bracket pi, which is pi over 3 plus 2k pi divided by n, which is 2. So z is equal to square root of 4 is 2 times, let's do z of 0, that is k equals 0. So z of 0 equals square root of 4 is 2 times cos, then that means we will put k equals 0. If we put k equals 0, all this part goes to 0, so we'll be left with into bracket pi over 3 divided by 2 is pi over 6, then plus I sine into bracket pi over 3 divided by 2 here, 2 is pi over 6. So z naught is equal to 2 times cos pi over 6 is root 3 over 2, then sine pi over 6 is 1 over 2, so plus 1 over 2i. If you multiply through by 2, you see that z naught is equal to root 3 plus I. Having found z naught, let's find z1. So z1 is equal to square root of 4 is 2, and times cos, in this case, is going to be pi over 3 plus, then k is 1 here, so if you put in 1, 2 times 1 is 2 times pi, it will be 2 pi divided by n is 2, then plus I sine into bracket pi over 3 plus 2 pi divided by 2, bracket close. So z1 is equal to 2 times cos into bracket pi over 3 plus 2 pi is 7 pi over 6, and plus I sine, this place will be 7 pi over 6. But remember that we said for the principal argument, the value of theta is greater than minus pi but less than or equal to pi. You see that 7 pi over 6 is greater than pi, and therefore we must subtract 2 pi from 7 pi over 6. So theta in this case will be equal to 7 pi over 6 minus 2 pi, and this is equal to minus 5 pi over 6. So Z1 is equal to 2 into bracket cos. Now, cos minus A is equal to cos A, because cos is an even function. And then sine minus A is equal to minus sine A, because sine is an odd function. So this is equal to cos 5 pi over 6, then minus sine 5 pi over 6. So Z1 is equal to cos 5 pi over 6 is, so 2 times cos 5 pi over 6 is minus root 3 over 2. And then sine 5 pi over 6 is 1 over 2. So here too will be minus 1 over 2i. And therefore Z1 is equal to, if you multiply through by 2, it will give us minus root 3 minus I. So the root of this complex number is Z0 is equal to root 3 plus I, or Z1 is equal to minus root 3 minus I. So we have another question here, which says that find the fifth root of minus 1. In other words, Z exponent 5 is equal to minus 1. So we need to express minus 1 in terms of a complex number. However, if we sketch this on the real and imaginary axis, this is imaginary part of Z, and then this is the real part of Z. So if here is 1, then this place is minus 1. So therefore, minus 1 will be measuring the angle from here to this place. And therefore, you can see that the argument theta is equal to pi. So in terms of complex number, Z is equal to cos pi, then plus I sine pi. In terms of complex number, Z is equal to cos pi plus I sine pi. So therefore, Z exponent 5 is equal to cos pi plus I sine pi. So Zk is equal to the fifth root of 1, then times cos into bracket pi plus 2k pi divided by n is 5 in this case, plus I sine into bracket pi plus 2k pi divided by 5. However, we can see that k, the value of k starts from 0, 1 up to n minus 1. So in this case, k is 0, 1, 2, 3, 4. N minus 1 is 5 minus 1, which is 4. So therefore, these are the values of k. So let's find Z of 0. So Z of 0 means that wherever we see k in this equation, replace it with 0. So this is equal to the fifth root of 1 is 1, and therefore this is equal to cos into brackets pi plus 2k pi. The 2k part will go to 0, so pi over 5 plus I sine pi over 5. So Z0 is equal to cos pi over 5 is 0.81. Then sine pi over 5 is 0.59, so plus 0.59 I. So this is Z0. Let's come to Z1. So Z1 means that wherever we see k here, we replace it with 1. So it's going to give us pi plus 2 pi, which will be 3 pi over 5. So it's going to be cos into bracket 3 pi over 5 and plus I sine into bracket 3 pi over 5. So Z1 is equal to cos 3 pi over 5 is minus 0.31. Then sine 3 pi over 5 is 0.95 I. Let's find Z2. So wherever you see k here, you put in 2. 2 times 2 is 4. So it becomes pi plus 4 pi, which is 5 pi. So here is cos 5 pi over 5. Then plus I sine 5 pi over 5. 5 pi over 5 is pi. So this will give us cos pi. Then plus I sine pi. Cos pi is minus 1. Then sine pi is 0. So the answer just goes to minus 1. So Z2 is equal to minus 1. Let's do for Z3. Z3 is equal to, wherever you see k here, you put in 3. So 2 times 3 is 6. 6 pi plus pi is 7 pi. So Z3 is cos 7 pi over 5. Then plus I sine 7 pi over 5. However, you see that 7 pi over 5 is greater than pi. But we say that for the principal axis, theta is greater than minus pi, but less than or equal to pi. And therefore, the true value of theta in this case is going to give us 7 pi over 5. Then we subtract 2 pi from it. If we subtract 2 pi in this case, we are going to get pi equals minus 3 pi over 5. So Z3 is equal to cos to bracket 3 pi over 5, then minus I sine 3 pi over 5. Cos 3 pi over 5 is minus 0.31. Then minus sine 3 pi over 5 is 0.95. So minus 0.95 I. And let's do for the last one, which is Z4. So wherever you see k here, you replace it with 4. So 2 times 4 is 8. So pi plus 8 pi will give us 9 pi over 5. So cos 9 pi over 5. Then plus I sine 9 pi over 5. You see that in this case too, 9 pi over 5 is greater than pi. And therefore, we bring it into this range by subtracting 2 pi from it. So theta is equal to 9 pi over 5 minus 2 pi. And this is equal to minus pi. This is equal to minus pi over 2. So Z4 is equal to cos pi over 2, then minus I sine pi over 2. So this is Z4. Z4 therefore is equal to cos pi over 2 is 0. Then sine pi over 2 is 1. So this becomes 0 minus I. And therefore Z4 is equal to minus I. Find the cube root of Z equals minus 8 minus 8I. So let's convert minus 8 pi into polar form. R, which is equal to the magnitude of Z, is equal to square root of minus 8 squared plus minus 8 squared. And this is equal to square root of 64 plus 64. And this is equal to square root of 108. Square root of 108 is the same as 8 root 2. Let's represent it on an eigen diagram. So This is the real part of z. And then this is the imaginary part of z. So here is, let's assume this is minus 8. And this is also minus 8. So minus 8 minus 8 will be somewhere here. So this is z equals minus 8 minus 8i. Or if we draw this to this, you can see that here is theta. So tan theta is equal to the opposite, which is 8 over adjacent 8. So theta is equal to tan inverse of 8 over 8 is 1. Therefore, theta is equal to 45 degrees. But we know that we have to convert this into pi radians by multiplying by pi over 180 degrees. Therefore, theta is equal to pi over 4 radians. But remember that we measure the angles from here to this part. So theta is equal to pi over 4 plus pi. And theta is equal to 5 pi over 4. So z cubed. So z cubed is equal to 8 root 2 then times, in polar form, cos 5 pi over 4 and plus I sine 5 pi over 4. Now let's find the root. So zk is equal to cube root of 8 root 2 then times cos 5 pi over 4 then plus 2k pi divided by n, and n in this case is 3, plus I sine into bracket 5 pi over 4 plus 2k pi divided by n, and n is 3. So, but we know that in this case, the values of k will run from k equals 0, 1, and n minus 1, which is 3 minus 1. 3 minus 1 is 2. So we are going to find z of 0, z of 1, and z of 2. So let's find z of 0. This is equal to cube root of 8 root 2 is 2.24. And this is equal to, now, if you put 0 here, you will find out that this part will go to 0. So it will be 5 pi over 4 divided by 3, which will give us 5 pi over 12. Sorry, cos 5 pi over 12, then plus I sine, and here will also be 5 pi over 12. So z naught, z of 0 is equal to 2.24 times cos 5 pi over 12 will give you 0.58. Sorry. So z of 0 is equal to 2.24 times cos 5 pi over 12 is 0.26, and plus sine 5 pi over 12 is 0.97i. So if you multiply by 2.24, then z of 0 will give 0.58 plus 2.17i. So let's do z of 1. Z of 1 is cube root of 8 root 2 is 2.24 times, wherever you see k here, you put in 1. So it becomes 5 pi over 4 plus 2 times 1 is 2 times pi, 2 pi. So 5 pi over 4 plus 2 pi, all divided by 3. So here becomes cos into bracket 13 pi over 12, then plus I sine 13 pi over 12. But 13 pi over 12 is greater than pi. But theta must be less than minus pi, must be greater than minus pi but less than or equal to pi. So what we need to do is that we need to find the correct value of theta in this case. So this will be 13 pi over 12. Then you subtract 2 pi. If you subtract 2 pi from 13 pi over 12, you will get minus 11 pi over 12. So Z1 is equal to 2.24 times cos into bracket 11 pi over 12, then minus I sine into bracket 11 pi over 12. So Z1 is equal to 2.24 times cos 11 pi over 12 is minus 0.966, then minus sine 11 pi over 12 is 0.26 I. So Z1 is equal to, if we multiply 2.24 by minus 0.966, it will give minus 2.17 minus 0.58 I. Let's look for Z2. Z2 is equal to, so 2 times 2 is 4 pi. 5 pi over 4 plus 4 pi is equal to, all divided by 3 will give 21 pi over 12. So Z2 is equal to 2.24 into bracket. Wherever you see k here, you insert 2. So 2 times 2 is 4. So 5 pi over 4 plus 4 pi is equal to 21 pi over 3. Because it is 5 pi over 4 plus 4 pi over 3. All over 3. So 21 pi. So here's cos. Sorry, I forgot the cos. Cos 21 pi over 3. And plus I sine 21 pi over 3. But you can see that, over 12. So it's rather 21 pi over 12. And so you can see that 21 pi over 12 is greater than pi. So therefore, we can find the true value of theta by subtracting 2 pi from 21 pi over 12. And this is equal to minus 3 pi over 12. So Z2 is equal to 2.24 into bracket cos 3 pi over 12, then minus I sine 3 pi over 12. So Z2 is equal to 2.24 into bracket cos 3 pi over 12 is 0.707. Then minus sine 3 pi over 12 is 0.707 I. So Z2 is equal to 1.58. 2.24 times 0.707 is 1.58. Then 2.24 times minus 0.707i is minus 1.58 I. Show that 1 plus I is a root of the equation z exponent 4 equals minus 4. Find each of the other roots in the form a plus bi, where a and b are real. Plot the roots on an argand diagram. By considering the diagonals, or otherwise, show that the points are at the vertex of a square. Calculate the area of the square. So let's write z equals minus 4 in terms of polar coordinates. If we sketch this, so you see that imaginary axis of z, the real axis of z. So that means that we are going to measure all the way from here to that place. And therefore, you can see that the argument of z is equal to pi. So therefore, z in terms of a complex number is r, Let's find r. R is equal to the square root of minus 4 squared plus 0 squared, because this can also be written as minus 4 plus 0i, and this is equal to 4. So z is equal to 4 into bracket cos pi plus I sine pi, bracket close. So this implies that z exponent 4 is equal to 4 into bracket cos pi plus I sine pi. So z is equal to the fourth root of 4. So zk then times cos into bracket pi plus 2k pi divided by n, and n in this case is 4, plus I sine into bracket pi plus 2k pi divided by n, which is also 4, bracket close. Sorry, I made a mistake, because here is minus 4 and z exponent. So here is minus 4, and therefore here is fourth root of minus 4. Now let's solve it here. The fourth root of minus 4. This can also be written as minus 4 exponent 1 over 4. And minus 4 can be written as minus 2 squared exponent 1 over 4. So this is the same as these two cancel 1 over 4, and this is the same as minus 2 exponent 1 over 2, which is equal to root minus 2. And root minus 2 is equal to root 2i. So z of k, which is equal to the fourth root of minus 4, is equal to root 2i times cos into bracket pi plus 2k pi divided by 4, then plus I sine into bracket pi plus 2k pi divided by 4. So we've established that z of k is equal to root 2i times cos pi plus 2k pi over 4 plus I sine pi plus 2k pi over 4. But we know that it is z exponent 4, and therefore k will go from 0, 1, 2, and then n minus 1, which is 4 minus 1, which is 3. So let's find z of 0. Wherever you see k here, put in 0. So root 2i times cos into bracket. Now this part will go to 0, so it will just be pi over 4 plus I sine into bracket pi over 4. And this is equal to root 2i into bracket cos pi over 4 is 1 over root 2, then plus sine pi over 4 is 1 over root 2i. So z naught is equal to, if you multiply through by root 2, and you are going to get minus 1, then plus I. Now you can see that root 2i times 1 over root 2, root 2 and root 2 will cancel. So here we'll be left with I, which is this one. But here is root 2i times 1 over root 2. So it's going to be root 2 over 2 times I squared. But I squared is minus 1. Let's solve for z1. So this is equal to, wherever you see 1, you put in, wherever you see k, you put in 1. So this will be root 2i into bracket cos. Now 2 times 2 is 4, 4 pi. So pi plus 4 pi is 5 pi over 4. 5 pi over 4 plus I sine 5 pi over 4. But you can see that 5 pi over 4 is greater than pi. but theta must be greater than minus pi but less than or equal to pi. So we need to subtract 2 pi from 5 pi over 4. So 5 pi over 4 minus 2 pi is equal to minus 3 pi over 4. So Z1 is equal to root 2i into bracket cos. Then minus 3 pi over 4 will be 3 pi over 4 because cos is an even function. Minus I sine 3 pi over 4. So Z1 is equal to root 2i, then into brackets cos 3 pi over 4 is equal to minus 1 over root 2. Then sine 3 pi over 4 is minus 1 over root 2. So here will be minus 1 over root 2i. So root 2i times minus 1 over root 2 is equal to minus I. And then root 2i times 1 over root 2i will give minus I squared, which is equal to I. And therefore Z1 is equal to 1 minus I. So this is Z1. So let's solve for, so let me write it here. So therefore Z1 is equal to 1 minus I. Let's solve for Z2. Z2 is equal to, wherever you see k here, you put in 2. So 2 times 2 is 4. Pi plus 4 pi is 5 pi. Sorry, I made a mistake. This is for Z2 because 2 times 2 is 4. 4 pi plus pi is 5 pi. So here is Z2. And therefore, this is the value for Z2. Now let's do for Z1. So Z1 is equal to, wherever you see k, you put in 1. So it's going to be pi plus 2 times 1 is 2. So pi plus 2 pi is 3 pi. So here is going to be 3 pi over 4. And therefore it's going to be root 2 times cos 3 pi over 4 plus I sine 3 pi over 4. So Z1 is equal to, here is root 2i. So root 2i, then to bracket cos 3 pi over 4 is minus 1 over root 2. Then sine 3 pi over 4 is 1 over root 2i. So Z1 is equal to root 2i times minus 1 over root 2 is equal to minus I. Then root 2i times 1 over root 2i is equal to minus 1. So Z1 is equal to minus 1 minus I. So let's do the last one, which is Z3. Wherever we see k here, we'll insert 3. So 2 times 3 is 6. So pi plus 6 pi is equal to 7 pi over 4. So Z3 is equal to root 2i times cos 7 pi over 4, then plus I sine into bracket 7 pi over 4. So we can see that in this case too, 7 pi over 4 is greater than pi. So we subtract 2 pi. If we subtract 2 pi, we'll get minus pi over 4. So Z3 is equal to root 2i and to bracket cos pi over 4 and minus I sine pi over 4. So Z3 is equal to root 2i then to bracket cos pi over 4 is 1 over root 2, then minus sine pi over 4 is minus, is also 1 over root 2. So here will be 1 over root 2i. So Z3 is equal to root 2i times 1 over root 2 is I. Then root 2i times minus 1 over root 2 is equal to minus 1 times I squared, which will give us plus 1. So therefore Z3 is equal to 1 plus I. And this was what the question was saying we should prove. So this is the proof. The proof is Z3. Z3 is 1 plus I. And then the other roots are. So at the end of the day, you see that we have 4 roots. Z of 0 is equal to minus 1 plus I. Z of 1 is equal to minus 1 minus I. And then Z of 2 is equal to 1 minus I. And then Z of 3 is equal to 1 plus I. Now let's represent this 4 on an Argand diagram, because that was what the question said we should do. So let me sketch the Argand diagram here. This is the imaginary part of Z, and this is the real part of Z. So let's assume here is 1 and here is minus 1, and here is minus 1, and then here is 1. So when we take Z0 is minus 1 and then 1. So you see that minus 1 and 1, they will meet somewhere here. Here is Z0 equals to minus 1 plus I. And then Z1 is minus 1 minus I. So minus 1 minus I is here. So here is Z1 equals to minus 1 minus I. Then Z2 is 1 minus I. So this is 1 minus I. So this is 1 minus I. And that is Z2 equals 1 minus I. And then Z3 is 1 plus I. This is 1 plus I. So it's somewhere here. And this is Z3 equals 1 plus I. So at the end of the day, just as we were asked to prove, you can see that these are the vertices of a square. So this is the square. Now, the last part of the question says we should find the area of the square. So you can see that since it is a square, then all the lengths are equal, and the area of a square is given as L squared. So the length is the distance from here to this place. But you see that if you move up, it's 1 unit, and if you move down, it's 1 unit. So moving from down to up will be 1 unit plus another unit, and that will be 2 units. So L is equal to 2, and therefore A is equal to 2 squared. Therefore, the area is equal to 4 units.